Hello, I am Václav Novotný and welcome to the tutorial of energy sources and conversions. This tutorial will be focused on Brighten cycle, the cycle of gas turbine. So let's have a look how the Brighten cycle works. Here you can see the process flow diagram where the Brighten cycle consists of compressor, turbine and two heat exchangers. The working fluid at the point number 1 goes through the compressor where the pressure is increased. Then between points number 2 and 3 there is heat addition. From point 3 to 4 there is expansion of the working fluid in turbine which produces work, and then between points 4 and 1 is heat rejection. With the thermodynamic states, the change 1 to 2 is isentropic in the ideal case, 2 to 3 is isobaric heat addition, 3 to 4 is isentropic expansion, and 4 to 1 is isobaric heat rejection. So you can see the changes are the same as were for the Rankine cycle, just the difference in here is that this is the cycle where the working fluid is always in the gaseous form. We can see that in the TS diagram over here, where we don't see any phase change. The isobars are smooth curves without any sharp change, which would happen in the change of phase. And we start at the point 1, where in the ideal case the ideal compression is isentrope, where we need to put in some work so that we compress the working fluid between points 1 and 2. Following on that is isobaric heat addition to the point 3. From point 3 to point number 4 is isentropic expansion, where we produce the work, and 4 to 1 is isobaric heat rejection. Similarly, we can draw also the diagrams in the PV coordinates, pressure and unit volume, where the isentropes or reverse adiabatic changes are these curves, 1 to 2 and then 3 to 4. And then we have two isobaric changes here at P2 for heat addition and at P1 for heat rejection. This is the ideal representation of Brighten cycle as a closed cycle, but typically in real applications we are having open Brighten cycle. What does it mean? We take the air from the ambient conditions, which is basically a huge reservoir at certain temperature. Then we have the compression. Heat addition is typically performed as a combustion chamber where the fuel is combusted with the air and the temperature increases. Then expansion takes place in the turbine between the pressure 3 and the pressure 4, which is ambient, and that means the working fluid is exhausted into the atmosphere. So in the TS and PV diagrams we can see that the cycle is so-called closed by the atmosphere, and therefore this heat rejection does not happen in any heat exchanger, but the, let's say, nearly infinite reservoir of the environment works for this heat rejection. So this is the change in points 4 to 1 over here and in the diagram over here. Now let's have a look at some parameters of the Brighten cycle. The defining parameters of Brighten cycle are basically the temperature levels, the typically temperature at point 1, in the open cycle it's the temperature of the ambient air, and then temperature 3, which is the firing temperature, the maximum temperature of the heat addition, typically given by parameters of the combustors like temperature limits, their specifications with respect to emissions like nitrogen emissions, and so on. Then the second defining parameter are the pressure levels, where typically we have the pressure 1 and also pressure 2 given by the atmospheric air, so that's fixed. And then we have the high pressure in the cycle. And since this pressure is fixed, so it's quite comfortable to define the pressure at the point 2, the pressure of the heat addition, by the so-called compression ratio, P, which is the ratio of the pressure P2 over pressure P1. Typically, this pressure ratio is somewhere between values of 10 and 30, where for large-scale gas turbines, let's say with hundreds of megawatts, typically you can find value around 24, 25. And then, on the other hand, for micro applications of so-called micro turbines, which have other features, so-called regeneration, which we will talk about later on, they have very small pressure ratios, let's say between 2 and 6. Now, our calculations will be performed with not just ideal gas, but also perfect gas. That means ideal gas with constant specific heat capacity. And the defining equations will be for these three changes. For the isentropic change, heat input and output, which are the isobars, and then work input and output, which are the isentropes. So for the isentropic, or other words, reverse adiabatic change, we will use the expression for the ratio of the temperatures T2 over T1 over here, which is the P2 over P1 to adiabatic exponent kappa minus 1 over kappa. How to get to this relationship? Well, we can derive it from the ideal gas equation PV equals RT, where we can manipulate the variables and get that the R equals PV over T. The R needs to be constant for any state of the fluid, so it needs to be valid for both state 1 and also the state 2. And then the second equation is the equation of the reverse adiabatic change, where PV to kappa is constant. That means, again, for any state any state of the working fluid which happens to be on the isentrope, PV to kappa needs to be constant, so P1 V1 to kappa equals P2 P2 to kappa. So first, let's do some manipulation with the equation over here. So we can write that T2 over T1 will be P2 over P1 times V2 over V1. We can additionally do now we can take this equation of the reverse adiabatic change or isentropic change, and we can write that P1 over P2 is P1 over P1 over P2 will be V2 over V1 and raised to the kappa. Okay, now what we can do about this is that we take the inverse value, and the inverse value from this will be that we switch the P1 and P2 to P2 over P1, and the right hand side, if we take the inverse value, so it also works that we change the sign in front of the exponent. Okay, now what we can do also is that we raise both sides, left hand side and right hand side, to the same value. So it will work in a way that for us, that let's raise it to minus 1 over kappa, or 1 over minus kappa. So it will look like this. Here we will have 1 over minus kappa and by this we will also multiply this one over here. So what we will get, minus kappa divided by minus kappa is 1, so this will be just 1, and here we are having P2 over P1 to 1 over minus kappa, which can be also expressed as minus 1 divided by kappa, like this. Okay, now let's take this expression and insert it in the equation here. So V2 over V1 is this over here, and the P2 over P1 can be also written as P2 over P1 raised to the 1 to the power of 1, so basically like this. But this one can be also expressed as kappa over kappa, and now we can put these two parts together, and it will look like T2 over T1 is P2 over P1 to kappa minus 1 over here divided by kappa. And this is the expression that we had over here. Okay, now for the heat input and output, so those are isobars. So in isobaric change, the heat or the change of the heat is the change of enthalpies, and the change in the enthalpy in the ideal gas is Cp dt, specific heat capacity times change of the temperature. And since we will consider the heat capacity to be constant, because we will consider perfect gas, so change of the heat or the transferred heat will be Cp times delta T. Similarly, it will work with the work input and output, because the isentropes for the isentropes the work can be expressed again as change in the enthalpy. And as we are in ideal gas, so change in the enthalpy, the H would be specific heat capacity times change in temperature. And because the specific heat capacity will be again in our case constant, so we can also write it as differential, as not just differential but difference, that the work will be the Cp constant times difference in temperature. And now we can move to our first example calculation, where we will explore the Brighton cycle parameters based on firing temperature, where we will assume ideal gas, first ideal gas, no efficiency of the components, or ideal efficiency, meaning 1, no pressure drops. Ideal air would be the working fluid. The specific heat capacity will be constant. Then we will have specified the isentropic exponent, kappa, as 1.4, typical value for free atomic gas. Inlet parameters at the compressor intake will be temperature 15 degrees C and pressure 0.1 megapascals. And firing temperature will be constant, T3, 1100 degrees C. Now our task is to get at first the limiting pressure ratio when this temperature 1100 would be reached already at the outlet of the compressor, and then get the parameters as cycle efficiency and unit work as a function of the pressure ratio in the range of pressure ratios 1 to 30. So for the limiting pressure ratio, let's use the expression over here and just transform it in the way that we will get the exponent to the left hand side. So we can move the kappa minus 1 over kappa over here while taking the inverse of it, so it would be kappa over kappa minus 1. So T2 over T1 is P2 over P1 times kappa to kappa minus 1. And if we want to get the limiting pressure ratio where the temperature T2 after compression will be 1100 degrees C, so we can write that the P2 is this P1 multiplied by this member over here. So it looks like this. Now the temperature T2 was specified as 1100 degrees C, which is 1100 plus 273.15 kelvins. The temperature T1 as the ambient temperature was specified as 15 degrees C, which is 15 plus 273.15, which is 288.15 kelvins. Now the pressure P1 was specified as 0.1 megapascals, and because we are working with the pressure ratios, again this is just basically want to get the pressure ratio P2 over P1, so we don't need to use the basic SI units, but we can still just work with the megapascals, so just use them directly. Alright, so now the P2 will be 0.1 times temperature T2 over here divided by temperature T1 and this raised to the kappa, which is 1.4 divided by kappa minus 1. And we should get the pressure P2 to be 23.6 megapascals, which also means that the pressure ratio would be 236. And we have said before that the pressure ratio range is about, let's say, 10 to 30, definitely much less than this one over here. So this really extreme pressure ratio would cause that the temperature at the compressor outlet would be already 1100 degrees C, but it's far away from typical values of Brayton cycle. Now let's do a calculation for illustrational pressure ratio, which would be, let's say, 10, and we will get the Brighten cycle parameters: heat input, heat output, work input and work output. So first we will get the temperature after the compressor, so it will be that the temperature T2 will be temperature at T1 multiplied by P2 over P1 to kappa minus 1 over kappa, which is temperature T1 288.15 multiplied by, now the P2 over P1 is the pressure ratio, PR, so in our case it's 10, and kappa was 1.4, so it's 1.4 minus 1, 0.4 divided by 1.4. So we will get the temperature after compression as 556.3306 kelvins. Now the temperature T3 was already given, it was 1100. The temperature T4 can be obtained with the same method as over here because it's isentropic expansion. So same as we had T2 and points 2 and 1, so we can have points 4 and 3 before and after the expansion. So now T4 is T3 multiplied by, now here would be pressure 4 over pressure 3 to kappa minus 1 over kappa. Now the pressure 4 over pressure 3 is 1 over the pressure ratio, like this, and we get that the temperature 2 is temperature 3, which is the firing temperature 1100 degrees C. You can write it over here. Before it was that extreme case of calculating that pressure ratio for having the temperature already after the compression. Now we are far from that, but the temperature T3 stays constant from the problem statement, 1373.15 times 1 over pressure ratio, which is now 0.1, and raised to the exponent kappa minus 1 over kappa. Let's do it like this. And if we do the calculation, so we will get value of 711.2196 kelvins after expansion. So by that we have actually specified the temperatures everywhere in the cycle. Temperature 1 was given, temperature 2 after compression calculated here, temperature 3 firing temperature is given, and temperature at the outlet of the turbine is over here. So we can calculate the work of the compressor. Which is change in the enthalpy between points 2 and 1. Let's go ahead. Write it like this. Which in the ideal gas with constant specific heat capacity is the Cp times temperature T2 minus temperature T1. So now the Cp is 1.004 kilojoules per kilogram and Kelvin. And the temperature difference is T2 556.3 minus T1 over here 288.15 kelvins which calculated together will be 269.2533, and we have kilojoules per kilogram. Here, so kilojoules stay, kilograms stay, and just the kelvins will cancel out. So we have the specific work, 269 kilojoules per kilogram of the compressor. Now for the turbine. The work of the turbine is change of the enthalpy before and after the turbine, so that means enthalpy H3 minus enthalpy H4. Which here in our ideal perfect gas constant heat capacity Cp times temperature T3 minus temperature T4. So 1.004 times temperature T3, the firing temperature was over here, 1373 kelvins, minus temperature T4 over here, and we get work of the turbine as 664.5782 kilojoules per kilogram of working fluid of the air. So the net work of the cycle or the work of the cycle, that's probably the way to call it, will be work of the turbine minus work of the compressor which will be work of the turbine over here minus work of the compressor which is 395.3249 kilojoules per kilogram. Now similar approach will be taken for the heat input and output. So heat input will be change of enthalpy between points 3 and 2. So it will be Cp times T3 minus T2, which will be 1.004 times temperature T3 divided by minus temperature T2 and it will be 820.0867 kilojoules per kilogram. And the heat output from the cycle, the rejected heat, will be enthalpy H4 minus enthalpy H1, outlet of the turbine minus the inlet of the compressor, which will be Cp times T4 minus T1 and numbers 1.004 times temperature T4 over here minus temperature T1 and we will get 424.7618 kilojoules per kilogram. Now we can calculate the efficiency of the cycle. Which can be calculated as the work of the cycle divided by heat input well, which is work of the cycle is in here 395 kilojoules per kilogram, and the heat input is 820 kilojoules per kilogram. And we will get the efficiency of the ideal Brighten cycle with pressure ratio of 10 being 0.4825. 48205. So 48%. The results that we have just calculated are for the pressure ratio of 10. But we can use the same method for basically any other pressure ratio. So for example, if we implement it in spreadsheet, where we have given the temperature with respect to, we have the fixed values over here, the constants, kappa, the isentropic exponent, specific heat capacity, inlet temperature and the firing temperature, and then the respective values are referenced to the constants and eventually to other parameters. So here we have temperature T2, here we have temperature T4, here we have the work of the compressor, the unit work of the expander of the turbine. The difference between the two of them is the work of the cycle. The heat input is the difference in temperatures, firing temperature and the temperature T2 multiplied by the heat capacity. The heat output, difference in heat capacity times temperatures T4 and T1. And finally, the efficiency is the ratio of work of the cycle divided by heat input. Or also, just to make sure, we can also check that the efficiency would be the heat input minus heat output, Q in minus Q out, divided by the heat input. And you can see that these values are identical. But now when we have these functions implemented here, so we can basically extend it both up and down to lower pressure ratios and to higher pressure ratios, where obviously for pressure ratio of 1 there is no compression, the temperature goes down to T4, but well, no pressure difference, so no work of the compressor, also no work of the turbine, and therefore heat input and heat output is the same and the efficiency is 0. Then as the pressure ratio increases, so we can see that the temperature after the compressor is going up, then the temperature after the turbine is actually going down. Work of the compressor is increasing, work of the turbine as well, and for the unit heat input, heat output, and the work of the cycle, we will see how it works, also how it works with the efficiency. So we can we can show the efficiency of the system with respect to the pressure ratio as a chart, and we can see that as the pressure ratio increases, so the efficiency goes up, but the beginning part is much sharper than the subsequent part at the high pressure ratios. Now let's have a look also how it works with the work of the cycle per 1 kilogram of working fluid, where you can see that as the efficiency steadily increases, so the unit work per 1 kilogram per second of the working fluid has a maximum about pressure ratios somewhere around 15. Okay, so this was the first example in our tutorial. Now we will calculate a very similar example, but with efficiency of components as turbine and compressor. So the problem statement stays nearly the same, just we have one last point over here. The compressor isentropic efficiency is 80% and the turbine isentropic efficiency is 90%. The rest of the example remains the same, and now let's implement it in our calculation. So for the isentropic efficiency, let's recall also from the last tutorial on Rankine cycle that for the isentropic efficiency of the turbine, it's the ratio of the real work output to the ideal work output. In matter of enthalpies, it was enthalpy difference of real expansion in ratio to enthalpy difference of ideal expansion. Now we can write this thing in here in this example with ideal or even perfect gas, also in matter of temperatures and specific capacity. So the expansion at the turbine takes place from points 3 to 2. From points 3 to 4. So it would be Cp times T3 minus T4 real. That's the real enthalpy difference, and the enthalpy difference for ideal expansion would be Cp times T3 minus T4, or we could also write T4 isentropic. It would be expansion is 0.4 and here was 0.3. In the last tutorial we expressed the enthalpy after the expander as the enthalpy before the expander minus the ideal enthalpy difference multiplied by the efficiency of the turbine. The same can obviously work also with the temperatures because the specific heat capacity is constant, and since it's constant, so we can just cancel it out over here, and we can write that the temperature at point 4, let's call it for real, is temperature at point 3 minus ideal difference in enthalpies multiplied by turbine isentropic efficiency. Now let's let's put it in the values from our example with the pressure ratio being 10. So the enthalpy at the point 3 was the firing temperature over here, 1373, minus now the temperature difference, temperature at point 3 minus temperature at point 4 with the ideal expansion, and now this is multiplied by the isentropic efficiency of the turbine, which was 90%. So it will go like this. And while the former temperature after the expansion was 711 degrees C, so now it will be 777.41 degrees C Kelvins. Very similar approach is at the compressor, where the efficiency of the compressor was defined as the ideal work divided by the real work, because the ideal work is smaller than necessary work to use in the compressor. In matter of enthalpies, it was difference in ideal enthalpy over difference in real enthalpy, and basically the same way it can be also expressed with the enthalpy as with the perfect gas as Cp times difference in temperature. So in our case, compressor is between points 2 and 1, so it will be Cp times T2 minus T1, where the T2 over here is ideal or isentropic. And here we have real difference in enthalpies, so it will be Cp2 Cp times T2 real minus T1. Then we could express the enthalpy after the compression for the real compression as function, or as enthalpy before the compression plus the ideal difference in enthalpies divided by the efficiency of the compressor. Now, because also the CPs can cancel out because they are here assumed to be constant, so we can write this in temperatures, that temperature 2, let's say temperature 2 after a real compression will be temperature T1 plus ideal difference in temperatures divided by efficiency of the compressor. So temperature T1 was 288.15 plus now temperature difference, temperature 2 was over here, 556 kelvins minus 288.15, and this difference in temperatures was or needs to be divided by the compressor efficiency, 80%, so that this member will get higher, and you will see that the outlet of the compressor is at a higher temperature. And after the calculation, we will get the temperature after the compressor to be 623.376 kelvins. Now the work and efficiencies of the system will work basically the same. So starting with the compressor work, Cp times delta T, Cp stays the same. The temperature difference, temperature T2 after the compressor, we just calculated that it's not 556, but that it's 622. So the work of the compressor in this case will be 336.57 kilojoules per kilogram. Then the work of the turbine, again Cp times delta T, Cp stays the same, temperature T3 stays the same, and it's just temperature T4 that is now different, temperature after the expansion, which instead of original value 711 is now 777. So the work of the turbine will be smaller than before. Before it was 664 kilojoules per kilogram, and now it will be 598.12 kilojoules per kilogram. The work of the cycle is the difference of these two, so 598 minus 336, and we get the work of the cycle as 261.55 kilojoules per kilogram instead of the original value 395. So you can see quite significant decrease. Let's have a look at the heat input. The heat input Cp times T3 over T3 minus T2. So temperature T3 over here minus temperature T2 and the heat input is 752.77 kilojoules per kilogram instead of the original value being 820. So you can actually see that the heat input is slightly lower because of the efficiency, and we will see later on the TS diagram why is it like that. And the heat rejection, also Cp stays the same, times difference in temperature, temperature T4 is now higher. Minus temperature T1 stays the same, 288 kelvins. And the value of heat rejection is 491.22 kilojoules per Kelvin instead of original value 424. So the heat rejection is larger, the heat input is just a little bit smaller. The efficiency of the cycle, work of the cycle over here, and the heat input in here. Same efficiency would be also a result of getting the work of the cycle from the balance heat input minus the heat output. You can check it for yourself. And the resulting efficiency is 34.75%. So quite a significant decrease compared to the original value of 48%. And this is because of the efficiency of the compressor 80% and of the turbine 90%. Okay, so the method of calculation that we just have shown can be implemented, for example, in the spreadsheet in order to get easily the values for different pressure ratios. So we have the temperature at the outlet of the compressor, where we use the original temperature after the compressor, the temperature at the point 1 at the compressor inlet, and here we have new parameters, efficiency of the turbine, and in this function used efficiency of the compressor. Similarly, efficiency of the expander results in new temperature T4. Then the work of the compressor is the difference in temperature before and after multiplied by the specific heat capacity. The work of the turbine, again, difference in temperatures before turbine or at the turbine inlet, at the turbine outlet, now for the real turbine with efficiency, and multiplied by the specific heat capacity Cp. Work of the cycle, difference of these two. Heat input is the difference before the or difference after the combustion chamber, firing temperature T3 minus real temperature T2 times Cp. Heat rejection Cp times temperature difference after the turbine and at the compressor inlet. And the efficiency is work of the cycle divided by heat input, or you can check that the same efficiency could be get as heat input minus heat output, which needs to be the work of the turbine divided by the heat input, and you can see the same values. Alright, so now let's compare these values to the original ones. So the temperature T2 over this one is higher. The temperature T4 compared to the original temperature T4 is also higher. We will see later on TS diagrams that it's because we are in higher entropies. Now the work of the compressor increased quite significantly from 270 to 330, while the work of the turbine decreased from 660 to 598, almost basically 600. Work of the cycle is therefore significantly lower. The heat input, we will see later on the TS diagram why, got a little bit lower from 820 to 752, but the heat output increased quite significantly and the efficiency dropped from 48% by about 13 percentage points to 35%. Now just don't forget in your functions to log respective cells from the boundary conditions. So it would be here. Here we have the efficiency also to be logged. This should be okay. We'll check. So the temperature T2, temperature T4, and the other parameters go like this and this. Okay, so now let's see what happens with the real compression and expansion, where the parameters for this real efficiency of the components are the dashed values. So first let's have a look at the efficiency, where before the efficiency was steadily increasing. While now, when we have the efficiency of the real system, of the real components, so there is somewhere a maximum of the efficiency of the cycle, and it's actually around, let's say, between 20 and the pressure ratio between 20 and 25. And that is actually also the pressure ratio or the typical pressure ratio of gas turbines. Then the efficiency of the cycle is slightly decreasing. Now for the work of the cycle. So before we had some point of the maximum, where now the work of the cycle has the maximum at much lower pressure ratios, and generally the value is significantly lower. But probably the most important thing to take from this example is really the decrease of the efficiency of the real cycle with real efficiency of the components compared to the ideal cycle. Now let's have a look at the cycle in the TS diagram. So you can see over here that we have the temperature, entropy as the axis, and we have several isobars, where the first one is the isobar of the ambient pressure, and then further isobars at higher pressures. So let's say that the first one would be some low pressure ratio, maybe around 5, and the starting point would be over here with the ambient pressure, and let's say over here ambient temperature. Then for the ideal isentropic compression, we go to the point 2 over here. Then we have the constant heat addition up to the point with the firing temperature, which was set as constant. Let's say it would be somewhere over here. Temperature T3. So we have the heat addition all the way to this temperature T3. Then we have isentropic expansion to the point 4, and that is exhaust to ambient. The cycle is closed by atmosphere back to the point number 1. Now when the pressure ratio is increasing, let's have it for example in blue color, so the compression goes further up, and you can see that in the TS diagram the cycle is getting higher and not so narrow. So this would be 2.3 would be over here, and also you can see what we have seen in the results of calculation, that the point number 4 is getting into lower temperatures, and point number 2 is going into higher temperatures. Then eventually for high pressure ratios, the cycle would and 0.4, the cycle would look like this. Okay, so that's the effect of increasing the pressure ratio, of increasing the pressure of the heat addition. Now let's have a look at the case what happens if we have real efficiency of the components. Let's show it for example on the blue cycle in the middle at some intermediate pressure ratio, and the real compression or any real process in nature means that the overall entropy of the system is increasing, and we have entropy over here. So that means the compression to the point number 2 would not be vertical, but would go further right in the TS diagram, and it would look somewhat like this. So let's say that this would be point 2 real. Now the expansion from the point 3 to the ambient pressure again will go into higher entropies. So point 2 real would be over here. So what we can see, the point 2 real is at higher temperatures because it is at higher entropy, and also point 4 is at higher temperatures because it's at the points of higher entropy. Now let's have a look at one specific feature of the cycles with very low pressure ratios. Let's give here the cycle from the beginning, 1, 2, 3, 4, eventually with the real efficiencies of the components, so here would be 2 real, and here would be 4 after expansion in a real turbine with given efficiency. Now we can see that the temperature at the point 4, let's take the cycle with the real component efficiencies. So the temperature at the point 4 is much higher than is the temperature after the compressor. So it means that basically we should be able to take this amount of heat between points 4R and let's call it 5 as exhaust, and transfer this amount of heat into the heat input of the cycle and save some of the heat input, that not all the heat needs to be provided by fuel or by some other heat source. So this transferring of the heat from one part of the cycle to another, basically you could say it's a recycling of some part of the heat, is called recuperation or regeneration. Now here in this figure we have shown it with we have shown the maximum limits with the 0 temperature differences. When you have the real system, so you need to have always some temperature difference in the heat exchanger. So the heat goes from hot part to cold part. So there would need to be certain temperature difference like this, and the heat transfer would end up so because of the temperature difference, we would not heat up the high pressure air or high pressure gas to all the way to the temperature of T4R, but a little bit less. Similarly, we would need to finish the heat transfer at temperatures a little bit higher than is the temperature 2R. So here would be also some temperature difference. So let's call this point 5R, and for the heat input, let's call this point 2 REC as recuperated, and this would be real. Then for the ideal case of 0 temperature difference, this point would be 2 recuperated ideal, and this 5 would be 5 ideal. Now we will include the recuperation into our cycle calculations. The first thing that we will do is to draw a process flow diagram of this system. So we again start somewhere with the point 1. Following is the compressor. Then we have the recuperator heat exchanger. So let's draw a box between points 2, respectively to R, and to recuperated. Following on that is some combustion chamber, where we are combusting the fuel, or generally there is some heat addition. To the point 3, before the turbine. Then the working fluid expands in the turbine to the point 4, or in the real turbine to the 4R. Now the hot air or hot flue gas at the turbine outlet goes to the recuperator to transfer the part of its heat before it leaves to the environment at the point 5. Now what will change in our calculations? So the point number 3 still stays the same, nothing happens to the firing temperature. Point number 1, ambient temperature, ambient pressure also stays the same, nothing changed to the compressor, so point 2 also will remain as it was. So it's just this point to recuperate it, where we need to get the temperature, and then we have the combustion chamber. The point 3 will stay as it was, and therefore in the turbine also nothing will change. Point 4R, if we neglect any pressure drop in this heat exchanger in the recuperator, so point 4R will be on the same pressure, and there will be no change to the previous calculations. And after the heat exchanger, when the flue gas passes through it, we will get the point number 5. So we have these two unknowns points, where actually if we neglect any pressure drop, so the pressure will stay the same, and the unknown is just the temperature. Now, in the TS diagram, we have shown that the temperature is determined by some minimum temperature difference, by some delta T min. So the temperature at the point 2 REC will be temperature at the point 4, or for recuperated, minus this minimum temperature difference. And since our working fluid has the same specific heat capacity, both at the high pressure and low pressure and regardless of temperature, so the temperature difference on one side will be same as the temperature difference on the other side. So also the point 5, the temperature at the point 5 will be now temperature at the point 2, as we can see over here, plus the minimum temperature difference. Because the heat needs to go from the high temperature to low temperature, point 2 is the point at the low temperature, so point 5 needs to be higher. Point 4 is the point at the high temperature, so the point to recuperate it needs to be lower. So now let's see the problem statement for the recuperated Brighten cycle example. The parameters are same as for the previous task, just now we have added the recuperation, and we will explore at first the ideal state, the ideal cycle with the compressor and turbine having 100% efficiency, and the temperature difference in the heat exchanger being 0 kelvins. Then after that we will also have a look at the real cycle with the compressor efficiency of 80%, turbine 90%, and specified minimum temperature difference of 30 kelvins. The task stays the same, get the cycle efficiency and unit work as the function of the pressure ratio in the given range. As we have shown in the TS diagram and process flow diagram, in the recuperated cycle, the point number 1 stays the same, so the temperature 1 will remain the 15 degrees C, meaning 288.50 kelvins. Temperature number 2 after the compressor, since the compressor operates with the same pressure ratio and with the same starting point, so it will also be the same. So we can go back to get the temperature after the ideal compression, temperature T2, 556.3 kelvins. Now for the temperature to recuperate it, we will need to first get the outlet of the turbine. The temperature T3 at the turbine inlet stayed also the same. It was 1100 degrees C, which is also 1373 kelvins. The turbine operates between the temperature free and pressure given by the pressure ratio, that remains the same, and the ambient pressure, which also remains, because we have the same pressure ratio, so the ambient pressure stays also the same. So temperature T4 remains the same as also in the previous task. And the temperature 4 was 711 kelvins. Now we can get the temperature T2 recuperated, because we know that it was the temperature T4 minus the minimum temperature difference. Which in the case of the ideal cycle is the temperature 4 minus 0. And finally, the temperature at the outlet, temperature 5, after the recuperative heat exchanger, is the temperature at the point 2 plus minimum temperature difference. And since the minimum temperature difference is 0, so it will be same as the temperature at the point 2. If the specific heat capacity would not be the same, so we would need to make sure that the heat transfer between the points 2 and 2 recuperated and 4 and 5 would be the same. So we would need to check, or we would need to make sure that the enthalpy difference, enthalpy 3 minus enthalpy 2, enthalpy 2 recuperated minus enthalpy 2 would be the same as enthalpy 4 minus enthalpy 5. And then based on that we would see where is the bottleneck of the heat transfer, whether we can satisfy the minimum temperature difference rather at the high temperature or low temperature side of the cycle, apply that and then calculate the outlet at the other side. But because we have, in this case we have Cp constant, so we don't need to go through that. We have the temperatures at all points of the cycle. The work of the compressor, since the compressor remained the same, so work of the compressor is the same as the work of the compressor of unrecuperated cycle. So it was over here. Same will be actually the case of the work of the turbine and work of the cycle. Now for the heat input. The heat input is no longer the difference of enthalpies between points 3 and 2, but only between the enthalpy at the point 3 and enthalpy at the point 2 recuperated. So it will be the specific heat capacity times the difference in temperatures. Temperature 3 minus temperature 2. recuperated, which is 1.004 times temperature 3 minus, now the temperature to recuperated is 711 kelvins. And the result is 664.578 kilojoules per kilogram. Now for the rejected heat. Well, the heat rejection does not start directly at the turbine outlet, but at the point of the outlet from the cycle, which was denoted as 0.5, minus enthalpy at 0.1, which is Cp times temperature difference temperature. Minus temperature 1, which is 1.004 times difference in temperature T5, over here 556, minus 288, and the rejected heat is 269.25 kilojoules per kilogram. So if we compare these values to the original non-recuperated case, the heat input dropped from about 750 kilojoules per kilogram, and respectively the heat output dropped from 490 to 269 kilojoules per kilogram. The work of the cycle, the work of the turbine and compressor remains the same, so it should result in higher efficiency of the cycle. So for the efficiency of the cycle, the work of the cycle remains the same. The heat input is now lower. It's 664.578 kilojoules per Kelvin. And if we take the ratio of the work of the cycle to the heat input, we get the efficiency, which is in our case 59.49%. So it's actually quite dramatic increase compared to the previous efficiency of the cycle, which was about 48%. Now let's have a look to the modification of the calculation of the cycle with real efficiencies of the compressor, expander, and with given temperature differences. So the temperature T1 stays the same. Temperature T2 after the real compressor stays the same with previous real compressor calculation. Now after the recuperation, temperature to recuperated is temperature T4 at the outlet of the turbine minus the minimum temperature difference, where at the outlet of the turbine, same as at the inlet of the turbine, this was the specified temperature, and this calculated temperature is based on parameters that did not change. So these two temperatures also stay the same, and we can get the temperature 2 after recuperation, which is 777 minus 30 kelvins for minimum temperature difference, which is 747.41 kelvins. Now for the temperature at the outlet of the recuperator, temperature T5, the calculation is that it's temperature at T2, the temperature after the compressor plus the minimum temperature difference, so 623 plus the minimum temperature difference so that the heat can start flowing to the working fluid from the hot exhaust gas, and it's 653.376 kelvins. So as everything stayed in the compressor and turbine, it remains the same as for the calculation of the real cycle without the recuperation. same as for the work of the cycle. And now for the heat input, what changed was that the heat input takes place between points 3 and 2 recuperated. So the point 3 stays the same, but 2 recuperated is different from the previous point 2. And the heat input thus will be lower, and it will be 628.24 kilojoules per kilogram. The heat rejection doesn't take place anymore between the outlet of the turbine and point 1 at the beginning, but between the outlet of the recuperator, point 5. So the temperature at the outlet of the recuperator is over here, 653 kelvins, and the resulting rejected heat by the cycle is 366.687 kilojoules per kilogram. And finally we can get the efficiency of the cycle. Well, work of the cycle remained the same. What changed was the heat input. So we can calculate it like this. It needs to work in the same way as in the case that we would have heat input minus heat output as the work of the cycle, like this. And the resulting efficiency is 41.6%, which is about 7 percentage points higher than for the case without the recuperation. Let's have a look at the parameters of the cycle that we calculated as a function of the pressure ratio. We had the simple cycle in ideal form and with real efficiencies of the components already calculated before, and now we added the ideal cycle with recuperation and recuperated cycle with real efficiencies of the components and actual temperature difference. So let's have a look at the parameters as the efficiency and the work. For the work, of the cycle, as we said, it remains the same regardless of the recuperation. We have just two parts. It's the ideal cycle and the real cycle. Recuperated ideal cycle would have same work as the simple ideal cycle, and the recuperated cycle with real efficiencies would have the same work of the cycle as real simple cycle. Now for the efficiency of the 4 variations of the cycles that we calculated, we have here the efficiency of the ideal simple cycle, which increases over the whole range of the pressure ratios. Then the efficiency of the cycle with actual efficiencies of the components has the maximum around pressure ratio of somewhere, let's say 24, 25. Then when we have a look at the recuperated cycle, so the ideal one is over here, where we can see that actually the efficiency is decreasing with the pressure ratio. And when we add the efficiency of the components, so the curve is still decreasing and we have it over here. So you could say that, well, the recuperated cycle seems as the best option. Let's build only these and receive very high efficiency of the system. The problem is that at the low pressure ratios, the work of the cycle is rather low, so it would not be feasible for building large systems. And at the same time, we also neglected important thing, which are the pressure drops. And the pressure drops would actually show us that the maximum of the recuperated cycle can be somewhere around, let's say, 30-35% with the efficiency. So because of the actual limitations in the efficiencies also for the real cycle, if we take into account more of the effects and impacts, so the recuperation is not actually considered option for the big gas turbine systems. Now let's see what is actually this point from which the recuperated cycle appears to be worse than the simple one. Here for the ideal case, and here for the real case. So let's go back to the TS diagram of our cycle, which we have over here, and let's see what happens as we increase the pressure ratio from this one over here. Let's say somewhere in here. Here would be 0.2. Here we would have the heat addition, 2.3, and 0.4. Now what happened at this pressure ratio is that the temperature at the point 2 is basically the same as the temperature at the point 4. And this is the point where the recuperated heat is 0. And if we increase the pressure beyond this point, if you would have cycle with pressure ratio, let's say this high, so there is no space for the recuperation, but in the way that we have the recuperation defined, that the beginning of the recuperation is at the point 4. So what is actually happening is that we are transferring part of the heat over here, let's say up here, before we start the rejection of the heat back into the environment. So that would be the point where it really doesn't make sense to build such cycle, but we considered it in our calculation, and therefore the efficiency of the recuperated cycle dropped below the efficiency of the simple cycle. Alright, so that's all from the Brighten cycle tutorial, and hope you liked it, and see you at the next one.